we're now focused on the center of a galaxy, and looking at the Milky Way, if we zoom right in, we'll see the region shown on the right, which is taken with radio observations, and you can see some extended and interesting features, including the remnants of supernovas, and also just in general a high density of gas. And the supernova show that stars were born relatively recently, since the massive stars that ended in supernova had very short lives. So we also see some more recent star formation. But the interesting thing is on the left is tracing out the orbital paths of stars around the point that's called Sagittarius A star. And Sagittarius A star is also measured in radio waves. And if you have on the right, we see a relatively large extended region, but you can get very high angular resolution images to zoom right in and to pick out the details. And you see that this region is very small. It's at most about the size of the distance from Earth to the Sun, 1 AU. So it's a small distance. And what you see are these stars that are shown in the different colors, and these are observations that are taken over about 20 years, and well, actually more now that if we go up to the year 2020. And what you get is nice orbital paths. If you then just apply Kepler's third law for each of these, you can get a pretty good constraint on that central mass that these stars are orbiting around. And you see that it should be about 4 million times the mass of the Sun. So this is a very large mass in a very small region. And you could think that there might be 4 million stars packed into the size a little bit bigger than our own star somehow, but they should be extremely bright. However, you don't see that. In fact, it's a relatively dark region. And so the only thing that we know of that could have this high of a mass in that small of a region is a black hole. And so we have very strong evidence for it's called a supermassive black hole when we're talking about millions or even billions of times the mass of the Sun, as opposed to a stellar black hole, which has more of the mass of, say, 100 times the mass of our Sun. So we have a supermassive black hole. And when we look at other galaxies, we always see this in the center of every galaxy that we have good data on. We see a supermassive black hole. All right, so zooming back out again and looking at a galaxy as a whole, we can then think about how many galaxies fill a certain region of space. And we see that there is a relatively large volume that one galaxy will fit in. So if you then look at the number density, you get something like 10 to the minus 2 per megaparsec cubed. So this is, again, quite a large volume, but galaxies themselves are large. So you have a radius of a galaxy of about 50 kiloparsecs, And so you can follow the same method that we did when we looked at how likely it is for stars to collide. Now we're looking at galaxies colliding. And we can apply the same geometrical cross section, which is again this sort of circular area where now the radius is the radius of a whole galaxy, and we'll follow the same method that the average time between collisions of galaxies is related to this number density times the cross-section times this velocity that the galaxies are moving relative to each other. And because of this large cross-section, and also because they have pretty large velocities relative to each other of about 500 kilometers per second, then you get a value that is actually much shorter in time than it was for stars to collide. So this is more on the order of 5,000 gigayears. And that's still a long time, but of course this is not including the gravitational attraction. This is also an average number density, but there are often regions, and we'll see this next week, where you have clustering of galaxies, and in the center of these clusters, the number density becomes much higher. So in that case, the galaxies are closer together, and they're gravitationally drawn to each other. So when you consider all of those effects, then this time between collisions becomes closer to about 9 billion years, which is on the scale that we expect for the age of these galaxies. So we're now starting to think that it is much more likely that a large galaxy can collide with another galaxy. And we see something like 20% or so of these large galaxies do seem to actually collide. So this is looking much more likely. And the result seems to be that you end up with a merged galaxy, which is known as an elliptical galaxy. And the reason that these colliding galaxies do not just completely throw with orbital attraction and these tidal streams all of the stars and disperse is that, again, you do have the gravitational attraction that pulls them back together, and also because of that large distance between the stars and the very low probability that the stars inside of the colliding galaxies will actually smash into each other, you then have this idea that over time these galaxies pass through each other and settle down into a merged galaxy. So these are known as the result of mergers. And elliptical galaxies, there's an example shown on the bottom left, which interestingly has these dust lanes, or these kind of long streams of dust, which are a remnant, we think, of the two galaxies that collided. You see other elliptical galaxies where even this sort of remnant of the original galaxies is not evident, and you really see a uniform looking sphere or ellipsoid of stars and older gas. So when you look at this population of stars, it is mostly old. You don't see really any evidence of any young stars. The motion of the stars is random. You don't see these clear rotational motion that you would see in a spiral galaxy. And also, further, so both of those, you could argue, are evidence that they are the result of a merger. And the other bit of evidence, which is maybe more compelling, is that they are found in these denser regions of galaxy clusters where you would expect a higher number of mergers. All right, and we are going to end with active galaxies. And an active galaxy is basically a larger galaxy where you have good evidence that at the center of the galaxy, this supermassive black hole has formed an accretion disk. And you know that because you see this very high luminosity, and you can calculate what the luminosity should be if this accretion disk is operating at its near maximum efficiency, which is known as the Eddington limit, and you then get a luminosity which is actually brighter than the combined brightness of all of the stars in the galaxy. So, actually, brighter than the entire galaxy. Another thing which is very interesting and shown on the bottom left is that we think that these accretion disks are rotating, and we have a magnetic field which can be entangled, and along the rotational axis of the accretion disk, this twisted magnetic field can actually accelerate particles out perpendicular to the disk in these very large jets. So what you're looking at is the galaxy Centaurus A, and shown in purple are the radio and X-ray emission of these accelerated particles coming out of the jet, originating very close to the supermassive black hole in the center. And on the right is just a reminder of this schematic of an accretion disk following the exact same physics that we saw from stellar remnants that had accretion disks around either a neutron star or the smaller black hole that is the remnant of a star. And the exact same physics is in place, and so you can just use all of the same arguments that you saw, but then scale up what is that central object, and here it is a supermassive black hole that can be up to 1 billion times as massive as the sun.